All right, I want to give a little time today to talk about the concept of a slope field and its use in AP Calculus, AB. And the first thing I want to say is that it's something that's actually not at all necessary in your overall development as a calculus student. It can act as a nice aid in the understanding of the relationship between functions and their derivatives, or functions and their antiderivatives. So what we have in this example 8 is something that's telling us that the derivative of a function, dy dx, is 2x. And so we know from our study of differential calculus that that means that the slope of the function at any particular point can be given by the formula 2x. So you take the x-coordinate, you multiply it by 2, and that's what the slope is going to be. So what you will frequently be asked to do in an AP free response question is to draw a slope field based on a given differential equation. And again, a differential equation is essentially an equation that tells you about the derivative of some function. So what they're asking us to do is use all these points that are highlighted. Now we've got points all the way over to -3 going up to 2, -3 comma 2 is up here, -3, -2 is down here, all the way over to +3, 2, and +3, -2. So we've got 1, 2, 3, 4, 5, 6, 7 different x values and 1, 2, 3, 4, 5 different y values. We've got 35 different places where we can measure the slope of this thing. However, this particular differential equation, dy dx equals 2x, depends only on the x coordinate. So if I wanted to fill out this slope field, what I'd be doing is saying, okay, at the point -3, -2, in order to determine the slope there, I plug in the x-coordinate of -3 into that formula, and 2 times -3 is -6. So you can see that this y value played absolutely no role in determining this slope at that particular point. So all of these y values that are given, as you see, because the slope only depends on x, are going to be kind of meaningless. So for every single one of these points where x is -3, we know the y value, the slope, which represents the y value, is going to be -6. So I'm going to put in -6, -6, -6. Now, once our x values flip over and become -2 for these next series of points, we're talking about when x is -2. For these points right here, all we do is plug -2 in for this x. And 2 times -2, of course, is -4. So we're going to get a -4 here for all of these guys. Now, what that tells us is that, for example, at the point -3, -2, which we can go over here, -3, -2, so this point right here, we know that the slope of the curve at this point is -6. So what we'd be asked to do is to try to kind of draw a curve or draw a tangent line representing a slope of -6. Now, -6 is a fairly steep slope, so we're talking something about like that. And that's really all you do. You draw a little tick mark or a hash mark that indicates a slope of -6, which means kind of we're going down 6 and right 1. Of course, that's not, draw a scalar or something like that, but it's going to look something like that. And again, that's going to be the value of the slope for all of these points, which are all of these points here, where x equals -3. So I'm going to go and draw similar little tick marks to represent the slope of -6 at all those. Now, when we get to the places where x is -2, right here, these points, -2, -2, -2, -1, -2, 0, -2, 1, and -2, 2, all those points, the slope is going to be -4. So I'm going to try to represent a slope of -4, which will maybe just look slightly less negative than that one before. And so what we're doing is we're building a field of slopes to kind of give us a picture of what this thing would look like. So you can see I've gone ahead and filled in the numeric value for the slopes at all the rest of these points, and our next job is to go ahead and give a picture of what those slopes would look like. So along the points where x is -1, these guys right here, the slope of the function is going to be -2. So I've got to come back to my curve and draw slopes of -2. So something maybe kind of like that. And at x equals 0, for all of these points, right in through here, you can see my slope is 0 because 2 times 0 is 0. So that means we're going to have horizontal tangent lines at all those points. So I come through and draw a horizontal tangent there. And then we get some slopes that are 2. Then we get some slopes that are 4, so make these a little steeper. And then lastly, some slopes that are 6. And what we now have is what's called a slope field. And what it does is it kind of gives us a picture of what the curve would actually look like. A curve, a collection of curves would look like whose derivative is 2x. Now, it doesn't take a whole lot of work to say, hey, if dy dx is 2x, that means dy can be represented by 2x dx. And we could find y by finding the antiderivative of 2x dx, which would be x squared plus a constant. And everybody watching this video knows what x squared looks like. So it would be a curve that would have a look something like this. And what you see is that the slope field has kind of predicted what my curve would look like. Now, if I had a curve, for example, y equals x squared minus 2, that would be a situation where y of 0 would be negative 2. And that means I'd be hitting this point down here. So if I wanted to draw the solution to this particular curve, maybe I'll change colors for that, this curve where the value of the function is negative 2 when x is 0, I'd say, okay, well, I'm going to start here, and then I'm just going to follow my slope fields to give me a picture of what this thing is going to look like. And of course, we're just mapping out what we know that function would look like. So there you go. Very typical, where you just have to kind of plot a bunch of slopes at different points along a coordinate plane, and it kind of, when you're finished with it, it gives you a picture of what the graph would look like, the original function would look like. So a completed slope field, as you can see down in these guys, what you're looking at is the actual function that has a derivative given by some formula. So for example, this function here, letter A, looks like maybe a sine or a cosine. It certainly has that look, where the slope appears to be 0 right at the where x is 0. So we'd be looking for an equation, a differential equation, that looks trigonometric, like maybe number 3 or number 4 here, where the value of the slope is going to be 0 when x is 0. If we look at this guy, the cosine of 0 is 1. And this thing does not look like it has slopes of 1. This guy does not look like it has slopes of 1 when x is 0. However, this one does. Looks like it has a slope of 0 at 0 because the sine of 0 is 0. So I would be ready to commit myself and say, hey, this really looks like the sine of x. If you start to connect these dashes, you get something that looks like that, and it certainly looks like a sinusoid. You say, okay, that's what I'm committing to. So we would say A is number 4. So then you look at example B here, you say, okay, this slope field kind of gives us a picture of something that kind of looks like this. Kind of looks like the parabola we just made in that first example above. And you say, okay, over on the side you see these things that look virtually vertical. And that's because by the time this thing gets out here, that slope is going to be so big that it's going to appear as a vertical segment here. But basically we're looking for a function that's going to look like that. Which, might be x squared or x to the 4th. Now, when you see these choices down here, a sucker answer for this one might be option 1, that the derivative is x squared. However, remember, when we're looking at this picture, this is a picture of what the function would look like, not what its derivative would look like. So what that's going to do is say, hey, this guy over here, if dy dx is 1/4 of x cubed, you could say, well, that means dy is 1/4 of x cubed dx, and if I were to find the antiderivative of that, it's going to be 1/4 of x to the 4th over 4 plus c, which is x to the 4th over 16 plus c. And there we go. There's a function that's going to have that look. So let's say that this guy is option 6, and we'll cross him off. The other approach to doing these is saying, rather than trying to think of the antiderivative of these things, trying to think of the antiderivative of each one of these functions and finding a function that looks like that, is just use the idea that here's a formula for the slope. So for example, if I'm thinking about 2 over x, obviously at x equals 0, this thing is going to be undefined. So I'm looking for something that maybe has a vertical asymptote looking thing at x equals 0, which this certainly looks like it has. But more specifically, if x were, say, at x equals -1, that would mean my slope would be 2 over -1, which is -2. And I say, okay, well, at x equals -1, looks like my slopes are -2. But at x equals +1, we get 2 over +1, which is 2. So coming over here at +1, we get all these slopes that look like they're +2. And that's starting to make a really good case for this thing. And you could say, well, by the time I get out here to the end, when x is, say, maybe something like 6, that means my slope is going to be 2 over 6, which is 1/3. So now at the end, I should have a very shallow slope of maybe 1/3 by the time that x equals 6. And similarly, when x equals -6, that would lead to a slope of -1/3, which, again, looks like we have out here. So we can have a really good idea that that guy is number 2, and we have one more to go. And the one thing I would say in looking at option D here is that all these slopes seem to be positive. First, it's kind of painting this look of this function going like this. You say, wow, that looks like exponential growth. And it sure as heck isn't cosine. And this option 5 looks very positive for it, because for all values of x, e to the x is going to be positive. It'll just be slightly positive when e is a negative. When x is a negative number, and it's going to be very, very positive when x is a positive number. So, kind of painting a picture of this guy's function here that kind of goes like that. Sure looks like that function is e to the x, whose derivative, the derivative, of course, of e to the x, is e to the x. So that's this guy. So we can say he's option 5. So, we didn't use this one and this one, but both of those two guys were sucker answers for, this one x squared looked like it could have been the choice for B if you weren't thinking about the actual function instead of its derivative, as far as what you're looking at. And then the cosine one as well, because its derivative is sine, as opposed to sine, which is the derivative of cosine. So there's a couple of good matching examples. Now, to finish up this unit on slope fields, this little section on slope fields, I wanted to look at an example that came from a AP free response question from a few years back. And the first two parts of this, A and B, I've highlighted here that we're going to walk through right now. And I think you'll get a sense that these are pretty doable problems. I would say when you get to an AP free response question, you should feel fortunate if one of them is a slope field question, because they're pretty straightforward in the approach. The first thing they ask us to do is sketch the slope field at the 12 points indicated. So you can see this is a 4x3 grid, so there's 12 points across the way here. And it would probably be a good idea. The safest thing to do with these things is to literally list the coordinates of all those 12 points, and then use the x and the y values in this formula, and that's going to generate the actual value of the slope. Okay, so I took a little time to write out all the coordinates of all 12 points, and all we're going to do now is determine the slope at each point by plugging, for this first one, -1 for x and 0 for y into this little formula. And when x is -1, we're going to get -1 times 0 minus 1 over 4. So that's -1 times -1, which is 1 over 4. So we get a slope of 1/4. So at the point -1, 0, we have a slope of 1/4. So maybe I'll change color and try to draw a slope of 1/4 there. So it's just slightly positive. Moving along, when x is -1 and y is 1, you're going to get -1 times 1 minus 1 over 4, which is going to be -1 times 0 over 4, which of course is 0. So at this second point here, -1, 1, we get a slope of 0. So I draw a little horizontal tangent line there. In fact, we should recognize that any point on this curve where y is 1, so that's this one and this one, we are going to get a horizontal tangent, because when you plug a y equals 1 into this part of the formula, you're going to get the 0 for the slope. Similarly, when x is 0, our slope is going to be 0. So when x is 0, that means all these points right along here where we haven't moved left or right. So I'm going to go ahead and add those in as 0 slopes. 0 slope, 0 slope, 0 slope. And now it's just up to us to go figure out the slopes at those 5 remaining points, and we'll be good to go to be able to have the whole thing drawn. Okay, so now I've got the rest of the slopes computed. So at -1, 2, -1, 2, we have a slope of -1/4, and at -1, 3 up here, we have a slope of -2/4, or -1/2. So I can draw those in there and say, let's see, -1/4 is just slightly negative, and -1/2 is a little bit more negative, something like that. At 1, 0, we're talking about a slope of -1/4. So we can make that slope of -1/4 there. And then we've got slopes of +1/4 and +1/2. So you may finish this slope field here, and you look at it and say, my gosh, I've never seen a function that has any kind of curve that looks anything like this. Don't worry about that, because with this derivative being what it is, it's likely this is some kind of funky hyperbola that might have a look like this, going up and down like that, or up and down like that. And we haven't studied a whole lot of their graphs, so it's not too surprising that you wouldn't recognize its slope field. But again, you're just picking up points for literally some basic arithmetic and a little quick sketch. So that's why I say these are kind of friendly as far as free response questions go. And also, I should say it's not too common to have to fill out 12 of these things. A lot of times it's only about 6 or 9, maybe 6, 7, 8, 9, 10 points, something like that you'd have to fill out those little tangent lines for. Now, part B of this basically allows us to have a little connection between a couple of different things we've done. So if there's some particular solution to this differential equation where f of 1 equals 3, that would be, this point up here. That's wonderful that we know that it's that point, but it really doesn't matter that much. We know that there's a point at 1, 3 on this curve, and they're asking us to approximate the value of f of 1.4. Now notice, that's a point that's going to be close to that particular value at 1, 3. So what we know is that there's this curve that kind of has this point here at 1, 3, and it has this sort of look to it like our slope field sort of has, of maybe looking something like that at that point. And they're asking us to determine the equation of the tangent line at that point to approximate what f of 1.4 would be. So if you could imagine a tangent line coming along here and hitting this curve like that, they're saying, okay, well, in actuality, there's a point on the curve at 1.4 over here where we have no idea what the y value is, but we could certainly approximate its value with this point here on the tangent line. So we should be able to figure out what that is if we can get the equation of this line. But again, about 100 times this year we've talked about what do you need if you're going to write the equation of a line, and we need two things. We need a point, and we need a slope. And the point, of course, is 1, 3, and the slope, we already did the work. The slope at 1, 3 is 2/4, otherwise known as a half. And so I'll say the slope is 1/2. So the equation of that line is y minus 3 equals 1/2 times x minus 1. And remember early on I said don't be intimidated by these linear approximations. All you're doing is using the tangent line to come up with the approximate value of a function at a particular point that's close to the point of tangency. So when you bring that over, you say, okay, bring that 3 over to the other side, you get 3 plus 1/2 of the quantity x minus 1, and we could think of that y as being like our linear approximation, 3 plus 1/2 of x minus 1. So thinking about L of 1.4, that just means we're going to plug 1.4 in. So 3 plus 1/2 of 1.4 minus 1. So of course that's just 1/2 of 4/10, which is 1/2 of 2/5. So 3 plus 1/2 of 2/5. So the 2's cancel and we get 3 plus 1/5, or you want to write that as 16/5, or you could write it as 3.2. It really doesn't matter. So we're going to say our approximation is 3.2 or 16/5. Very typical. They could follow up and say, is that an overestimate or an underestimate of the actual value of the function there? Now, it looks like from my picture that it's an underestimate. In other words, this y value is less than that y value. But to generally answer that question, you would need the second derivative, which they're not going to do on this because this second derivative is going to get kind of nasty. But if they ever give you a simple one, the way to verify whether it's an underestimate or an overestimate is you think about the second derivative, its concavity. So if it's concave down, your tangent line would be riding above it, and it would be an overestimate. If it's concave up, your tangent line would be underneath, and it would be an underestimate. But there you go. There's slope fields, example of a free response question. Again, not too hard, just a lot of arithmetic and understanding what it's telling you.